So this is part 5 and this is the final part from the year 2021, and here we are going to solve 3 questions, and all these 3 questions are from the advance. Previously in the first 4 part we only solved the question which were from the mains. So this is the final part 5th for the year 2021. So first question, it states that in the circuit shown below, the switch S is connected to position P for a long time so that the charge on the capacitor becomes Q1 microcoulomb. Then switch S is switched to a position Q. After a long time, the charge on the capacitor is Q2 microcoulomb. So based on this, we are having 2 parts and we are supposed to find out the magnitude of Q1 and magnitude of Q2. Basic circuit is given to us. We are given 2 battery sources, 1 volt as well as 2 volt, and switch S is there and it is first connected to point P and then it will be connected to point Q. Okay, so when it is connected to point P, the charge on the capacitor is our Q1, and when it is connected to point Q, the charge on the capacitor is Q2, which we are supposed to find out both values, Q1 as well as Q2. So let us solve it to the first part when switch S is connected to P. Is connected to P. So we can just draw the approximate circuit. And we have to keep in mind that in both cases, the position of the switch is for a considerable long time. And under that condition, we can say that long time basically is steady state condition. So a capacitor will be acting as an open circuit. So let us suppose this is our R1, R2, V1, V2, and we have capacitor, this is C. So here this capacitor C is our open circuit. So every resistance is R1, R2, V1 as well as V2. Therefore, we can write that under steady state condition, capacitor, which we assumed in this case is C, is open circuit. So obviously no current will be flowing through this particular capacitor, and we have 2 voltage sources, and let us assume we are given V1 is our 1 volt and V2 is our 2 volt. So for the sake of convenience, let us assume that the current is flowing in this direction and its value is our I1. And so here also it will be current of I1. So this end will be positive, negative, and this end also positive as well as negative. And let us call this as A, B, C, D, E, and F. So we are going to use KVL in the loop A, B, A, C, D, F. So you can see Kirchhoff voltage law in A, B, C, D, E, F and back to A. And the loop, we assume that we are taking in this direction. So this is the direction of the loop. So let's start with our V2 voltage. So this is rise in potential. So this will be our plus V2. And then it will be minus I1 times R2 because of fall in potential. Similarly, minus I1 R1, and we have minus V1 is equal to 0. And we already know a value of V2. V2 is our 2 volt. So we get this as 2. I1 we can take as common. We get this as R1 plus R2. And R1 plus R2 is our 1 plus 2 minus this is 1 volt is equal to 0. So from here we get that the value of current, that is our I1, will be equal to, this is our 1 by 3 amperes. See, we got the current that is flowing in the loop, that is our 1 by 3. And we are supposed to find out the charge. So in order to find out the charge on the capacitor, we need to find out what will be the voltage drop across this capacitor, that is a VC. And this VC will be equal to our VB minus VE. And here let us assume that we have a voltage drop of VA, and here at C let us suppose that is a VC. Okay. So obviously our VA will be equal to 1 volt and VC will be equal to 2 volt. Okay. So let me redraw this figure. We are only interested in voltages, so I'm going to draw only half of the circuit. So this is our point A, point B and point C. We have our VA, VB as well as VC. Here we are having our R1 as well as our R2, and current is, we know, is flowing from right to left. Value of the current is our, that is our I1. And this VA is our 1 volt and VC is our 2 volt. So for this circuit part for AB, we can write the equation, that the equation will be our current is flowing from the, should be flowing ideally from higher potential to lower potential. Therefore we can write the equation that our VB minus VA should be equal to 1 second. Okay, so this is plus and this is minus. Similarly, this is plus and this is minus, and will be equal to our I1 multiplied by R1. And similarly, for the other side also, we can write that our VC minus VB will be equal to I1 times R2. And we are interested in VB, and we can write that our VA is, okay, So let me try to sort it out. This is a VB, VA is our 1 volt, is equal to I1 is our 1 by 3 and R1 is our, one second, R1 is our 1. So we get, so from here we get that our VB will be equal to 1 by 3 plus 1, which gives us 4 by 3. Same value we are going to get from this part also. Okay. So we get our VB is 4 by 3 volt. And the lower end is obviously our zero potential. So the voltage drop across the capacitor, that is VC, will be equal to VB minus VE. So we can write voltage drop across capacitor voltage drop across capacitor, that is VC, is our VB minus VE, which gives us 4 by 3 minus 0. So we get our VC is equal to 4 by 3 volts. So we got the voltage drop across the capacitor. Now we can easily find out the charge. Charge in the first case is set to our Q1, that is charge on capacitor C, that will be equal to our VC multiplied by the value of the capacitance, that is our, which is given to us as 1 microfarad. So we get this as 4 by 3 into 1 microfarad. So this gives us that our Q1 is equal to 4 by 3 microcoulomb. So we get our Q1 is 4 by 3 microcoulomb. Now for Q2 switch S is connected with Q. So we have our switch S is connected with Q. So therefore our circuit will be coming something like this. Now in this case we are only going to have one voltage source in the circuit, and capacitance once again will be open circuit. So this is R1, we have R2, voltage is V2, V1 is short circuited or not connected to the circuit basically, and this is our 2 volt. So here also under steady state condition capacitor C will be open. Under steady state capacitor C is open circuit. And let's find out, same we are going to find out the value of the current, and in this case let us assume that the current flowing is our I2. Here we can just use the equivalent part, no need to use KVL. So we can say our current I2 will be equal to our V2 divided by R equivalent. R equivalent is our series combination of R1 plus R2. So this comes as V2 R1 plus R2. So we get that our I2 will be equal to 2 divided by, and this comes as 1 plus 2, giving us 2 by 3 amperes. So once again, we have let us call this as A prime now. This point let us call A prime. This is our B, C, D, E and F. No doubt A prime and F will be at same because they are short, but anyways, for the clarification, let us write it like that only. And once again we are going to draw the circuit. We are interested in finding out VB. So this is our VA prime, this is our VB, and this is our VC. So once again we are going to draw only so this is A prime, we have B, and this is point C. Current I2 is flowing in this direction. So this will be plus minus, and we have this is R1 and this is our R2. So we call this as VA prime, this is our VB, and we have VC. Now VA here in this case will be equal to 0 because this entire potential is our 0. So VA prime will be 0. So we can just use the equation that VB minus VA prime, VB minus VA prime will be equal to I2 multiplied by R1. So we get this as VB is equal to I2 is our 2 by 3 and R1 is our 1. So we get our VB is equal to 2 by 3 volts. And in this case, let us assume the voltage across the capacitor is VC prime. So we can write voltage across the capacitor in this case we assume VC prime will be equal to VB minus VE. VE is 0, so this comes as 2 by 3. Now we can find out the charge on capacitor. That in this case our Q2 is charge on capacitor, which will be equal to VC prime multiplied by C. C is our 1 microfarad, so this comes as 2 by 3 microcoulomb. So we get this is equal to 2 by 3 microcoulomb. Next question. It states that 2-point charges minus q and plus q square root of 3 are placed in xy plane at origin and at a point 2, 0 respectively as shown in the figure. This result in equipotential circuit of radius r and potential V is equal to 0 in the xy plane with its center at b, 0. All lengths are measured in meters. So based on this we have two questions. The first we have to find out the value of r, and the second we have to find out the value of b. Okay. So basic figure is given to us. We are given 2-point charges. One is at the origin and other is at our 2, 0. So this point is our 2, 0. And this results in an equipotential circle of radius r. Okay. So it is going to have center somewhere here, and it says that its radius is our r with the center at b comma 0, and the coordinate of this point is our b comma 0. So we have to find out the value of b as well as the value of r. And here it says that the resultant potential of this minus q as well as this plus q root 3 result in the circle, so equipotential, and it says that at this on the circle the potential value is equal to 0. So from we can say that the net potential because of these two charges minus q as well as plus q root 3 will be 0. Okay, so we have to remember that. So first of all, let's write what are given to us. We are given two charges. We have a negative charge is given as minus q, and it is at origin. And then we have a positive charge is our plus q root 3, and it's placed at 2, 0. And the important part is that the potential along on this entire circle is equal to 0. So let us consider any point P on this circle, and its coordinate is of x, y. So let me write consider a point P whose coordinates are x, y on the circle. And we can find out the potential due to two charges at this particular point P. So we can say total electric potential due to two charges at point P, x, y. Let us call that potential as V, which is a function of both x and y, will be equal to, we have this as k will be our common, and we can write this as minus q upon r1 plus q square root of 3 divided by r2. And here our r1 is distance from the origin, because minus q is at origin, so r1 is our distance of point P from origin. Okay, so let me draw an approximate figure. So we are having, so this is our origin on the circle. We have considered a point P, and r1 is the distance of this circle, this point from the origin. So this is r1, and its coordinate is given as x, y. So obviously this height will be our y, and this distance will be our x. So it is basically 90° perpendicular. So from here you can say that our R1 will be equal to x square plus y square and its square root. Okay. And we have our R2. R2 is distance from two comma 0. So here we are having a point 2 comma 0, and this distance is our R2. So obviously this entire length is our, so we can say this distance will be about 2. So we can say this distance will be our x minus 2. Okay. And y will be our simple y. Okay. So we can say our R2 will be equal to x minus 2 whole square plus y square and its square root. And we are given that the potential on this entire circle is equal to 0. So we can substitute this v of xy is equal to 0. So we are given that potential on circle, which here is denoted as v of xy, is equal to 0. Let me write this as equation 1. So we can say from equation 1, we get this as minus 1 upon R1 plus 1 upon root 3 times R2 is equal to 0. So this basically gives us a relationship between R1 and R2. We get from R1 is equal to square root of 3 times R2. And so in this case, from this relationship between R1 and R2, we can write it that the locus of all points for which the distance from, because R1 represents the distance from the origin, so we can say from 0 comma 0 is root 3 times the distance from R2 represents the distance from 2 comma 0, from 2 comma 0. And this type of, you can say, circle is also called as a Apollonius circle. Okay, because the ratio, if I write that my R1 upon R2, let us define it as a ratio, then this ratio is equal to our, let's write it with capital R, sorry, we cannot write it capital R, let us keep it ratio only. Okay, so this R1 by R2 is a ratio, let's define it by C is equal to root 3. Okay. And this is, you can say, ratio is can be called as, so we can say this defines an Apollonius circle. Apollonius circle with its center and the formula of the center is our ratio is given as C, so this comes as C square x2 minus x1 divided by C square minus 1 comma 0. So this is the equation of the center. Similarly, we can write the equation for the radius, and the equation for the radius is our C upon C square minus 1 and its modulus multiplied by modulus of x2 minus x1. Now we already know the values. Our x1 is equal to 0 and our x2 is our 2 and our common ratio, that is C, is square root of 3. So obviously our C square is equal to 3. So we simply substitute the value. We get the center. In this center is represented in this particular case as B. So therefore we can write our B will be equal to C square, that is our 3 multiplied by 2 minus 0, and this comes as 3 minus 1 comma 0, which comes as 2 comma, I think this 3 comma, sorry, is it 3 to 6, 3 comma 0. And radius in this particular case is represented capital R, so therefore we can say our capital R will be equal to C is root 3 divided by C square, this is our 3 minus 1, and we have our 2 minus 0. So this gives us root 3 multiplied by 2 and divided by 2, which gives us root 3. So we got our radius is root 3 and value of B is our 3. Next question. It is basically a passage type question. It states that a special metal S conducts electricity without any resistance. A closed wire loop made of S does not allow any change in flux through itself by inducing a suitable current to generate a compensating flux. The induced current in the loop cannot decay due to its zero resistance. This current gives rise to a magnetic moment, which in turn repels the source of the magnetic field or flux. Consider a loop of radius A with its center at origin. A magnetic dipole of moment m is brought along the axis of this loop from infinity to a point at a distance r, which is much larger than A, from the center of the loop, with its north pole always facing the loop, as shown in the figure. The magnitude of the magnetic field of a dipole m at a point on axis is at a distance r is mu naught m divided by 2 pi r cube, where mu naught is the permeability of the free space. The magnitude of the force between two magnetic dipoles with magnetic moments m1 and m2 separated by a distance r on the common axis with their north pole facing each other is K M1 M2 divided by R4, where K is the constant of proportionality, appropriated dimension. The direction of this force is along the line joining the two dipoles. So based on this, we are given these two questions. So in the first part, it states that when the dipole M is placed at a distance r from the center of the loop as shown in the figure, the current induced to the loop will be proportional to. In the part 2, the work done by bringing the dipole from infinity to a distance r from the center of the loop given by the process is proportional to. Basic figure is given to us. We are having a loop of radius a and a dipole of dipole moment m pointing towards the loop, and it's placed at a distance of r. Okay. So basically, this is entire description is indirectly is telling us about the Lenz's law. Okay. It says that the loop opposes any change in the magnetic flux because it induces a permanent current that generates a opposite magnetic flux, magnetic field inside the loop. Okay, so this is the basic you can say concept around this discussion. And in the cases the first case we are given a magnetic field, and in the second case we are given the magnitude of the force in terms of the dipole moments m1 and m2. So we are going to use the equations for the you can say magnetic field because of the dipole. In the first case, we are going to find out the induced current of the loop is proportional to. So we have our part 1, and the dipole is on the axial line of the loop. So we can say the axial magnetic field from the dipole at a distance r. Let us call this as B dipole, and that magnetic field will be equal to over mu naught upon 2 pi r cube and multiply by the magnetic moment, okay, which is given to us. And this field is going to pass through the area of the loop, generating a flux through the loop. Okay. So we can say this field passes through the loop, and therefore the flux through the loop let us call this as flux as phi. So we can write the equation that the flux phi will be equal to magnetic field because of the dipole and multiply by the area of the loop. And we substitute, we get this a mu naught m 2 pi r cube and area is our pi a square. because radius is given as pi, radius is given as a of the loop. So here pi and pi cancels out, and this comes as our mu naught m a square upon 2r cube. And this loop, it induces the current that is going to oppose the flux. So you can say that as the loop is superconducting, it induces a current to cancel this flux. Cancel, or we can also say oppose this flux, which is nothing but our Lenz's law. So current, or rather let's write induced current. So induced current I must generate equal and opposite magnetic field. Through the loop. And we can use the standard formula for that. Magnetic field, because of the loop, will be equal to mu naught I upon 2a. Therefore, the flux induced in the loop, or we can say total flux through the loop, total flux through the loop, let us call this as phi total. So we can write our phi total, or let us call this phi induced, much better. So you can say phi induced will be equal to magnetic field because of the loop and the area, which gives us mu naught I upon 2a multiplied by pi square. Here square goes with this a, and we are left with this as mu naught pi a times I divided by 2. And this is equal and opposite through the loop. So we can say that equal and opposite due to loop flux. Let us call this as phi loop. Phi loop. Equal and opposite to phi loop. or we can say that our phi induced will be equal to our phi loop, which we can equate directly. Phi induced over mu naught pi ai divided by 2 is equal to mu naught ma square. Ma square divided by 2r cube. Here mu naught, 2 a goes with the square, it cancels out, so we get our value of current is equal to ma upon pi r cube, and we have to find out the proportionality. So we can say current is proportional to m upon r cube. So option number A is correct. Option A is correct. We come to the B part, and B part we are supposed to find out the work done. Part second, and obviously as the dipole is brought toward the loop, which induces a opposing dipole on the loop itself. So these two dipoles are going to interact. So we can find out the forces between two dipoles on a common axis. Basic formula is also given to us for that. So we can write that force between two dipoles on common axis let us suppose that is given as F, which will be equal to our K m1 m2, and we have this as r raised to power 4. And we can find out the induced magnetic moment. We can say induced magnetic moment, let us call this as m prime, and that will be equal to our, because we already solved our part A, so here let us call this as m prime, and this m prime will be proportional to current multiplied by A square. And current we already know, so therefore we can say our m prime is proportional to our m a cube upon r cube. Yes, I is our proportionality. Pi we can just simply remove it, so I is proportional to m prime is equal to m a cube upon r cube. So we can further write that our force in terms of the proportionality will be proportional to m multiplied by m prime divided by r4. We substitute the value, m is our m, we substitute over m prime, which comes as m a cube, and this is our r4 multiplied by r cube, which gives us our m square a cube divided by r raised to power 7. and we need to find out the work done. So we can say our work done to bringing dipole from infinity to r, from infinity to r. We can simply integrate. So we get W is equal to integration infinity to r, and this comes as F dr. In terms of proportionality, A will be over, because that circle is constant, only this M and R is going to change. So we are interested in infinity R. This comes as M square upon R raised to power 7 d of R, which is equal to, this comes as minus 1 upon 6, sorry, not 1 upon M upon M square, and this comes as R raised to power 6, and we have infinity to R, and this will be equal to M square 6R raised to power 6. Okay, so we need to find out the proportionality. So we can say our work done is proportional to M square upon R6. So we get this as M square upon R6. Option C is correct. Option C is correct. So these were the 3 questions which were asked in the year 2021 advance. So this completes the final part of this 2E from the year 2021. In the first 4 parts we did, or rather we can say we solved mains question, and this 5th part we solved only in the advanced questions. This completes all the questions from the year 2021. Thank you.